Yep.
Always learn.
I always joke that whatever class I'm teaching, I learn more than students do. But you guys are going to change that, right?
Fingers crossed.
Yeah. So it's nice to see far better attendance than I did last Friday. And even one who's not here let me know, but they would not be here, so that's good. Okay. Now, so I'm still kind of in travel mode. I just flew back in last night, so I'm always useless the first day after a trip, so this is going to be fun. Now, wow, this board is the worst shape I've ever seen it. I could pretty much read everybody else's lecture for the past 5 years on here. Oh, okay. Well, makes it even more interesting. Someone took the time to write out logarithm? Why? Okay, what you've learned, and hopefully not completely forgotten over a break, is, am I recording? Yes, okay. How to solve this kind of problem, y double prime plus py prime plus qy is equal to 0 with initial conditions. So the focus for this week that I meant to get started on, and only to a certain small extent did, last class was same kind of problem, although it's going to be a little more general. Allow the coefficients to depend on t. Although most of the time we'll only care about the case where they're constant. But now we have something non-zero on the right side, some given function g of t. And how can we use what we know about this in order to solve this? So what I'm going to do is show how we can come up with an approach to the solution, basically a solution formula that at least serves as a nice starting point for actual practical methods that you would use for homework or on a test. By taking what we know from here and finding a way to make it a little more general for this case. So in this case, where p and q are constants, we covered all the different cases, like you have a characteristic equation, you have your either real roots or complex roots or repeated roots, and you always had a form of a general solution. So by form of solution, I mean the general solution. And it was always some constant times y1 plus another constant times y2. So you always needed to find two generic solutions of this problem, and you'd use your characteristic equation for that. For instance, y1 might have been like e to the lambda 1t, and y2 would be e to the lambda 2t, if the roots lambda 1 and lambda 2 are real and distinct.
Is that for the non-homotopy?
No, I'm making a chart here.
Okay.
So this, yeah. So we're still in the review. Okay, so I'll segment this. So that form of a solution, though, where C1 and C2 are constants that are determined by the initial conditions, that form is not going to work for this because you find y1 and y2. It doesn't matter how you choose C1 and C2. You plug that into here on the right side, you're going to get 0. And now we want to get g of t instead. So obvious way to take this form, make it a little more flexible, a little more general to suit this purpose is we allow these parameters, C1 and C2, to be functions of t. So I'm going to call them W1 of t, Y1, plus W2 of t, Y2. I changed letters because I call it C1T, C2T. C automatically makes you think constant, and they're not in this case. So anything in this form is going to be also this form, but not the other way around. This allows more. So now these are unknowns. And we want to find formulas, if we can, for W1 and W2 that will satisfy this. So now what we can do is we can take this entire form and substitute into here. And I want to make sure, because there's a difficulty with this in last class, what does that really mean if we're taking some function of some form and substituting it into a differential equation? If I'm going to substitute that into here, what's the first thing I need to do? Yeah, and then? So yeah, I need the first and second derivatives, and then I can go ahead and plug this in here. Now it's going to be a pain in this case because W1, W2 are functions of t, so we have to use what? Yeah, we're going to have to use the product rule to handle all this differentiation. Okay. Now, so we go ahead and do that and see if we can simplify anything. Okay. All right. So y prime. All right, so this is going to get pretty ugly. So we're going to have W1 prime. I'm going to drop the of t just to save writing. But it's understood that everything in here is a function of t. So product rule for a first term, and then for a second term. Let's see. And then for the second derivative, I'm going to think, okay, now I have 4 terms. And the first derivative, I need to do product rule of each of those, giving me a total of 8 terms. But I'm not going to do that because I can economize a little bit. So if I go back to the original form of y and think in terms of what does the product rule mean for a second derivative? So because then you can combine like terms on the fly. So what you have is, if you take a second derivative of a product, it's going to be that plus, and then each one of these is going to produce a term of a form W1 prime, Y1 prime. And you might as well just combine them. And then I have W1 undifferentiated, Y1 double prime. So that leads to all of this. So I only have 3 terms from that part, and then I have similar 3 terms for y2, w2, y2. Notice how the order of differentiation of W1 keeps decreasing from left to right. Second derivative, first derivative, no derivative. And it's increasing from left to right for Y1. No derivative, first derivative, second derivative. So it keeps going like that. It's like when you're multiplying on a polynomial. Yes?
Shouldn't the...
Yes. Is that what you meant?
Yeah.
Yeah, okay. Thanks. Okay. So much easier when I'm typing notes, I just copy and paste. Of course, then I'm inviting different kinds of mistakes. Like some of these 2s would be 1s probably. And also look at the coefficients. 1, 2, 1. It's like when you're expanding, like you're expanding monomials to a certain power. Like if I had to take a third derivative of this, I'd have 4 terms. My coefficients would be 1, 3, 3, 1. Pascal's triangle is where all those coefficients come from. Okay, so now I have these 6 terms. Now I can substitute everything into my differential equation. And we have, okay, so I have y double prime okay. Plus p of t times y prime that I have here. Plus q of t times just plain old y, so that's w1, y1 plus w2, y2, and all of that is supposed to equal g of t. So now we have this huge mess, and we want to try to sort out from that how we can get formulas for w1 and w2. Now, what I can do is group these terms in such a way as to get some simplification. And I'm going to group them by order of derivative of w1 and w2. So first, let's see. I want to have all terms involving w1 double prime or w2 double prime. But there are only going to be two terms like that, these two. So I'll write those first. And my thinking here is I want to take advantage of the fact that y1 and y2 are already solutions of the original equation of 0 on the right-hand side. So I want to be able to take advantage of that. So here are all terms involving derivatives of w1, second derivatives of w1, w2. Now I'm going to look for terms that have first derivatives of w1 and w2. So for instance, I have this one, w1 prime, y1 prime. And then down here, I have terms involving w1 prime and w2 prime. And I'll factor p of t out of those. So we have w1 prime y1 plus w2 prime y2. Okay, so which terms have I dealt with so far? I've got that. Okay, I've written down that one and that one. Okay, so now I just have to get everything else. So I want to gather all terms that have just plain old w1, undifferentiated in them. So that's going to be w1, and I have y1 double prime plus p of t y1 prime plus q of t y1. Okay, and then I also, so now I've taken care of that, and that. And what's left, all terms that are not crossed out up above, have a w2 in them, undifferentiated. So I'll factor that out, and I have y double prime plus the y2 double prime plus p of t y2 prime plus q of t y2. And that has to equal, bless you, g of t. Okay. Now, seems like we have just as much of a mess as before. But y1 and y2 are solutions of the homogeneous form of the equation that has 0 on the right-hand side. So this is 0. This too, is 0. So all of those terms are now gone. So
You said Y1 and Y2 are solutions of the
this equation,
homogeneous term?
yes. Okay. Actually, for those of you watching at home, Y1 and Y2 solve this. So that's why we can replace those with 0. And now we can just take whatever terms are left. And what's interesting is now all the terms involving plain old W1 and W2 are gone. All we have left is W1 prime and W1 and 2 prime, and then also double prime. So we're not going to get formulas for W1 and W2. We're going to get formulas for W1 prime and W2 prime that satisfy a first order equation. And once we have that, then we can just integrate to get W1 and W2. So now, if we look at what's left, W1 prime, wait, yeah, W1 double prime, Y1 plus double prime, Y2 plus, okay. And also notice that Q is out of the picture. There's only P. Okay, so we still have G of T on
How
P.
is the Q out of the picture?
Oh, because Q was multiplying only terms like W1, Y1, W2, Y2. Any terms involving W1 or W2 not differentiated, those are included in what became 0. Q of T did not appear anywhere else. All right. Now, okay. I can define for convenience here Z to refer to this in here. So W1 prime Y1 plus W2 prime Y2. And the reason for that is, if you were to look at Z prime, so from this, what is Z prime? Just using product rule on this. W1 double prime Y1 plus okay, and then similar for W2. W2 double prime Y2 plus W2 prime Y2 prime. Now, these terms involving the second derivatives, you see up here. And these terms also you see up here, except here we have a coefficient of 1, here we have a coefficient of 2. So in other words, in all this mess right here, I can call most of that Z prime. And the only thing that's left is one of each of these. W1 prime, Y1 prime, plus W2 prime, Y2 prime. And then I have plus P of T times Z equal G of T. So now things are becoming more condensed. Now, so now what I'm going to do is I'm going to require, because I need to solve for W1 and W2, I have two unknowns. Therefore, I must have two equations to determine them completely. So for my first equation, I'm going to specify that z be equal to 0. Because if z is 0, then certainly z prime is going to be 0. So now everything on the left side is going to go away, except for this part on the left side. And I'm good to, okay, well first, z equals 0, this is z. So I'm going to write out what that means. So w1 prime y1 plus w2 prime y2 is 0. So that's z. And then, with this gone, I have this w1 prime y1 prime plus w2 prime y2 prime. This is gone. G of t is all that's left. So, now I have a system of two equations in two unknowns that are, my two unknowns are w1 prime and w2 prime. My coefficients are y1 and y2 in the first equation, y1 prime, y2 prime in the second equation. So, so what we can do is we can solve for w1 prime and w2 prime. Now, I should mention this system of equations, okay, that one, it has a unique solution if and only if the determinant of the coefficient matrix of this system is non-zero. The determinant is y1, y2, I just write down the coefficients from the two equations. And that must be non-zero. But does anyone know, what do we call that determinant? That's for Wronskian. Well, y1 and y2 are meant to be a fundamental set of solutions to the homogeneous equation. So they have a non-zero Wronskian. So we are short of getting a solution. Now, I won't go through the whole elimination and substitution process here, but if you did, here's what you would get. So W1, I can first remember Wronskian, I use this notation, capital W of y1 and y2, and that's a function of t. So we're going to solve for w1 prime, w2 prime, and then we're just going to integrate those to get w1 and w2. So w1 is going to be the integral of what you get for w1 prime from solving this system of equations. It turned out to be minus w2 of t, g of t, divided by the Wronskian, which is why the Wronskian had better be non-zero. Okay, so that's W1. Whoops. Sorry, that should be Y2, not W2. Okay. And then W, and that's a function of T. Make that dependence clear. And the W2 of T is an integral, and it's similar, Y1G over Wronskian dt. So notice your formula for W1 relies on Y2. Your formula for W2 relies on Y1, so that switches. Also, the formula for W1 has a minus, the formula for W2 does not. So once you find a solution to the homogeneous equation, you can just go ahead and work out these integrals, because from Y1 and Y2 you can get to Wronskian, and then hopefully it's something you can integrate. And there's your, and then you have a solution of your non-homogeneous equation. Now, because you're integrating, you have constants. And those constants can be determined by the initial conditions, like before. Now, so I did this to show you where a solution comes from. Now, in the this was done in the notes. Section 3.7. Now, there are two methods. Okay, so I want to let you know where we're at in the notes versus the textbook as far as learning particular methods for solving non-homogeneous equations.
Are we still at 3.3 or no?
No, 3.3 is long gone. That was complex roots. We not only that, we passed 3.4, which is on repeated roots. Okay, yeah, so 3.1 through 3.4, that's all in the homogeneous problem. Okay, so, all right, so now I'm going to let you know where we're at. Uh-oh. Okay, go, still recording. Now, in the notes, 3.5, okay, so the sections and notes are not exactly the same as the textbook, so keep in mind talking about the notes that I post on my resources page. This is about non-homogeneous equations in general. And that is very linear algebra intense. That's why I did not cover that here. So what it does is it goes through the three cases that we've seen: real roots, complex roots, repeated roots, and derives a solution formula in all three of those cases. And then uses similarities among them to arrive at the formulas that I just showed you here. And then 3.6, which corresponds to one section less in the textbook. All right, so just a little bit off, is the method of undetermined coefficients. And then 3.7, bless you, variation of parameters. Okay. Now, the method of undetermined coefficients is restricted to the case where P and Q are constants and only works for certain forms of g of t. Like it could be a polynomial, it could be exponential function or sine and cosine or products of any of those types, which covers a lot of functions, but there's still some that, quite a few that don't fall into that category. And variation of parameters is where you go ahead and compute W1 of t and W2 of t using the integral formulas I just wrote down. So that is the most general approach. But for a problem involving certain simplifications, like in this case, it might not still might not be the best way to go. Because it all depends on, can you evaluate the integral? And also, even if you can, what if it's a huge pain? Like involving all kinds of integration by parts, that we'd like to avoid that if we can. Now, the reason this method is called variation of parameters is, by parameters, I mean the C1 and C2. C1 and C2 are constants, and you have C1y1 plus C2y2 to make a general solution when there's no g of t. When there is a g of t, you let the parameters vary. That's where the name comes from. So by allowing these constants to instead be functions of t, we can now solve a non-homogeneous equation. So what I just did all this time on the board actually is worked out in section 3.7 in the notes. So the thing is, if P and Q are constant, then we know how to get y1 and y2. And second of all, if G is of a relatively simple form, meaning like polynomial, sine or cosine, or exponential, like with a like e to the at for some constant a, then then what happens if both of these are the case, p, q are constant and g is of its form, the integrals for w1 and w2, they're certainly doable, but extremely tedious. Definitely not the sort of thing I want you to have doing on a test. Certainly not the sort of thing you'd want to be doing on a test either, trust me. But since they're doable, if you already have some idea of what form they have, you get an idea about what the solution should look like. And in the notes, I go ahead and illustrate this for a few certain cases, how, okay, here's these integrals for W1 and W2. What do the integrals themselves look like when you actually carry out the integration by parts, etc.? So that if we know what this, so under these circumstances, the form of W1 and W2 can be known. So we say, okay, your yt is constant times this function plus another constant times this function, and then you can just find the constants. So W1 and W2 are known except for undetermined coefficients. So you take your form of your solution and substitute it into your differential equation. And you figure out what the constant should be so that it's satisfied. So in other words, there's very sensible reasons why these methods that I'm going to spend the rest of the week covering are named the way they are. That you're actually trying to find, trying to determine the coefficients, or in the other case, you're letting parameters vary to find solutions. So there are a number of problems that you could use either method for. But there's certain ones where method undetermined coefficients might be easier, and there's other problems where variation of parameters is the only option. So there's a good reason for looking at both of them. Okay, now, in the last 10 minutes, I want to set the stage for talking more about undetermined coefficients on Wednesday. Because what you know now is how to, for a case of a homogeneous equation, so there's no g of t, 0, you solve your characteristic equation, you get your roots, and based on the roots, you find solutions. And it's helpful if you know that process literally backwards and forwards. So given this characteristic equation, lambda squared plus p lambda plus q is equal to 0. I'm going to write down, oh, hold on, attendance. I'm going to write down some specific roots that could come from this equation. And I want you to tell me what the corresponding solutions would be. So for the first case, I'll write down roots. Let's say -1 and 3. So if you solve this equation for a particular differential equation, you get these roots. What are your solutions, y1 and y2? What would they be? Not C1, C2, just the functions that come out of this. Yeah, e to the minus t, e to the 3t. Okay. Now, suppose we have 2 plus or minus 3I. So we get two complex roots that are conjugates of each other. So who could tell me what y1 and y2 are in those cases?
Sine 2D.
So what?
Sine 2D and cosine 2D.
Nope.
E to the power.
Yeah, e to the 2t, the real part goes into an exponential, and then,
Cosine 3D.
yeah, the imaginary part goes into the argument of the cosine and sine. Okay. All right. Suppose you get a double root, 4 and 4.
E to the power 4t.
Mm-hmm.
4 e to the power 4. 4 e to the power. And t e to the power.
T, yeah, t e to the 4t. Okay. How about 2 and 0? Mm-hmm.
Yeah, wouldn't it be just one?
Yeah, because e to the 0t, but that's just 1. All right. Now let's try putting some of these situations together. What if you get a double root and both roots are equal to 0? So for instance, your equation was only y double prime equals 0.
Would it be 1 and t?
Yeah, 1, and then you multiply that by t, and you get t. So in other words, your solution is a linear function. It's a constant plus another constant times t, which makes sense because you have your equation is y double prime equals 0. If y double prime equals 0, then your solution has to be a linear function. Okay, so now, so the idea is your general solution of Ly is equal to G, where this is a second order differential operator. And I've defined this term before on more than one occasion. So if you do not remember what this means, I strongly urge you to look back in the notes, your notes or my notes. In my notes or the textbook, find section 3.2. Refresh your memory. And we have the solution breaks down into two parts. A solution of a homogeneous equation, Ly equals 0, plus what's called a particular solution of the non-homogeneous equation, Ly equals G. So undetermined coefficients and variation parameters are meant to find this part. But then you always add on to it a solution of your homogeneous equation, which will have this form. So we're going to have C1 y1 of t plus C2 y2 of t, the same kind of form you've had before, plus your particular solution, W1 y1 plus W2 y2. So C1 and C2 are constants that are determined by the initial condition. So when you get a non-homogeneous equation, especially if there are initial conditions involved, the very first thing you're going to do is you're going to find this first. So in other words, what you've already been doing in this chapter, you're going to do again. You're going to temporarily ignore the G and find this, but leave the constant C1 and C2 as constants. You don't determine them yet. Then you have to work on finding a particular solution. What you get for y1 and y2 determines, it influences what happens here. So it turns out for undetermined coefficients, it's actually going to be helpful to have a situation where not only are you finding roots and getting the corresponding functions, but now suppose G is of this form, one of these forms. How can you backtrack from functions like these to the corresponding roots. So you kind of, so the idea is for you to see patterns of, like if g of t is of, this form or this form, what roots does that correspond to? And that's what I'm going to have you look at. So we're going to do an activity at the start of class on Wednesday where you're literally going backwards and forwards to try to get this to become second nature. So think of it as being like a little quiz or something. No, it's not graded, but you want to do well on it anyway. Where given roots, get the solutions. Given solutions, get the corresponding roots. If you can train yourself to do that quickly, that will help you greatly in applying undetermined coefficients. It's one of the essential skills that you'll need to come up with the right form of the solution. Okay, so we'll close out by, since I'm packing up already, you can wait 2 minutes, I have 2 minutes. Suppose you have function g of t equals, let's say, e to the t sine 2t. So what roots of your characteristic equation would produce a solution that looks like that? Look at the patterns here to get an idea.
1.
Mm-hmm. That accounts for the e to the t.
Would it be
Plus or minus 2i, yes. So you see that, like it tells you, okay, a real part is 1. The sine and cosine of 2t tells you the imaginary part is 2. And you can have both roots, plus or minus, that you'll work with. Okay. And whereas if you have, for instance, g of t is equal to e to the 3t, what's the root that leads to that? Yeah, just 3. Okay. So going backwards and forwards like that can help you execute undetermined coefficients. I'll fill in the blanks on that method starting on Wednesday. All right.